Awesome. Cool. All right. Thanks everybody for coming out. Hopefully my clickbaity title got some of you here today. Well, my description and title was generated by Gemini. So, but no, for real, we are going to talk about a lot of fun stuff today. I think set expectations for the talk. We're going to talk a lot about technology stacks at a very high level. You know, there's a lot here to unpack. But the idea is hopefully you walk away from this with an understanding of why maybe not everyone's trying to train foundation models from scratch. You probably get why, there's probably a general consensus, but hopefully this gives you a kind of actually what really it takes to do such things. So with that, let me just kind of reintroduce myself. Like Mariah said, I've talked, actually my first talk here at the MLOps community was back in Jan 2020, right before the pandemic. I remember that. And I talked about improving artificial intelligence with human processes, right? Like being able to, and at the time I was working at Micron, Matt Sharp time. Also was in the Navy for a while. So before I joined back the engineering world, I was in the Navy, did nuclear engineering stuff. But I've been working in software and data since 2015. So that's just like a little bit about who I am, what I've been doing. Utah local Utah native as well. So enjoy the community. All right, let's talk about where we're headed today. So I want to start with defining foundation models. You know, what are they? What do we mean by foundation models? We all heard the terms like LLMs and things of that nature. Let's talk about foundation models and maybe why they're different or what they are. Some of the computational demands of foundation model training. So we're going to talk about, again, what does it take to actually train these things? I'll get into a little bit of paradigms of parallelism. These are talking about algorithms and things like that that allow you to actually kind of train in a parallel fashion, especially when memory is a constraint. Talk about collective operations as well, which makes a lot of this possible. A little bit of networking, not tons there, and then a little bit of software and infrastructure. But really the idea here is you guys walk away with this high level understanding of, all right, so these are all the things that kind of goes into training these very, very, very large models. And if you have a question, comment, whatever, just stop me. I'd rather have a discussion than just kind of talk at you. If you've done anything of this and you have something to comment on, I would love to hear your experience as well. Cool. Oh, I should probably say too. So currently working at Capital One. Been there for a bit. I managed a few different teams. I specifically work on their training platform for the enterprise. So specifically training model training. So that's both traditional ML and also now generative AI efforts. So that's fine tuning, things we'll get into today. So, all right. So foundation models. So what are they? What's kind of some key characteristics of this? Again, high level. Thinking about a foundation model, if you think about what do we mean by foundation model? It is anything that can be, it's a general, it has a general knowledge about something you fed it, and you can fine tune it, or you can give it a task to be better at one specific thing. Okay. So a lot of the LLMs that we use today, like ChatGPT, that is a specialized version of GPT, which is a foundation model. So again, we're talking about emergent abilities. We're talking about these models contain, they're not explicitly programmed, right? They're learned. They're actually self-supervised learning there, and they can learn from all different types. So that's what multimodal learning is going to be. So characteristics, right, that kind of set foundation models apart, and these have been going on for a long time now in terms of being able to, or companies looking in and researching into these. They're just really hitting this, right? So they're always trained on massive data sets. They're huge. They're trained on things like the internet, right? Things of large corpus of data. They're self-supervised. So you're just feeding in data, and the model itself has to learn and adapt to what is being fed into it. It's just creating a general understanding of whatever it is that you are feeding it. Overfitting is a really key part to this as well, to have it actually be part of to really embed this generalized knowledge into it. So the foundation model itself, overfitting is key there. And then you can generalize that to something specific task. Yes.
Discussion time.
Yes, that's it.
So normally overfitting's bad. It sounds like you're saying it's good here.
Yes. So you think about, I think there's people in this room that could probably ask this question a lot better than I can because I'm a platform guy. I'd say, Chris, what would your response be to that? I'm gonna put you on the hot spot. Yeah.
Oh, okay. So when your data sets are like literal trillions of tokens, that overfit is going to be like a much, what would you call that? Like it's not as sharp of a curve. Does that make sense? And so overfitting on trillions of tokens is good. Overfitting on hundreds of tokens is terrible. Does that make sense? And due to the, like, you can look up the chinchilla paper. It goes more into this for scaling laws for tokens to models and all of that.
So maybe that sounds like fitting.
Sure. Yeah. That's a good way to put it, right? I think, yeah, overfitting is used because it definitely kind of strays away from the traditional ML style of how you're training and what you're trying to get out of these models. But you're really just, again, it's because the corpus size, the data size is so large. You're looking at trying to explore all of that space to its fullest, not generalize too much to it. So you're looking for bias in the data set, in the model itself. So I did link. So I'm gonna, Mariah, I'll figure out how to get these slides up, but I do want, like, you guys can read like this block here. This gives a really good kind of overview of why this might be. The idea of the deeper discussion there.
You can always just share them in the machine learning channel in Slack if that's easiest. Put them on a Google Drive or just upload a file, that's fine.
So you guys can have a look at this presentation.
Just remember to join Forge Slack, forgeutah.tech, machine learning. I know the name's not AI, but you know, it's close.
Utah there. So, okay. I don't think you're fully satisfied with the answer to that question, but
I have a question, not a
Okay.
question.
okay.
Sorry, I'm thinking about the overfitting thing. Right, and so I'm thinking of I'm thinking of it in terms of your picture, and I'm at the correct me if I'm wrong state of this, right? So, right when we have a few parameters, the problem with overfitting is kind of like a noise to signal ratio, right? If we overfit on noise, we're missing the actual pattern that we're trying to define, right? But when you have trillions of parameters and you have the ability to actually accept and process the noise, like you're not saying, oh, find the signal in the noise. You're saying the noise is the signal, so you can be more accurate, right? Instead of finding a nice smooth curve, you're like, oh no, map the ridges, and that's how I'm thinking about it. Correct me if I'm wrong. I don't know. I'm just visual, and so I'm saying, okay, great. Instead of a nice, curve or wave or regression that you used to with classical machine learning that you don't want to overfit on, we've got a lot of data, and so we can be messy with it and get exacting, and it ends up being for this use case good. So anyway, correct. I don't know if that's right. That's just how I'm thinking about it.
I think that's a pretty good place to see. It's right here behind, yeah.
Overfit mean when you're self-supervised?
Really good question.
This is your sampling at the end of the model, right? Think of it in terms of code. I think that's the best place where this actually makes sense. These are syntax generators, and code syntax is incredibly rigid, right? If you are writing in Python, the beginning of your line, there's only a couple of things that it can be unless you're defining a variable. Like def will always be followed by some function name, right? What Mariah is talking about here, you are overfitting on specific scenarios within the data and then continuing on from them so it can replicate those specific scenarios, even though it has vocabulary of thousands and tens of thousands of words. Does that make sense? So overfitting in a self-supervised environment is, can you guess the next word in exactly the way that it wants you to and not generalize new data because you don't need to, right? You train on trillions of tokens, so the generalization is kind of out the window.
If it's about structure, it seems like constraint generation is better.
Oh, I agree.
Often you
I
would say
agree
it's not that overfitting is key, it's that overparameterization is key, right?
Yeah. Well, it's a combo, right? The big thing with LLMs, like Ryan was saying before, is the emergent capabilities, which is due completely to their scale, Right, this is the problem that flat earthers see, is the earth is such a huge scale that they can't see the curve. Think of that here, right? The amount of the data that they are training on is so huge that the curve is like minimum, and then it's still overfitting.
When I was writing this talk, or put this together, I didn't think that one right there would be, this is cool though.
Next time you give it, make sure you bring in
I'm
the.
gonna bring in your- I like the flat earth analogy. That was fantastic, by the way. That was really good. Okay. Do you have a question?
Oh, I was just gonna say, it's also like, they're often trained on more than one task. And so, that in itself introduces some regularization. As, I think that's actually crucial to it. So it does.
Yeah, it's like you're trying to map this whole space, this whole data space. You can't, 'cause you have so much, you have the room, the mathematical space to actually do that. So that's the idea. Any other questions about it? Talking about types of foundational models. So when we talk about these models in terms of what they're supposed to do and kind of like what their job is, they kind of look at them, and these are just high level categories, right? Talking about multimodal models, these are models that can take in one type of data and they spit out another, right? So if you have like stable diffusion, clip, dolly, those are examples of things that it takes in like a text generation potential or some other kind of input and replaces it with something else, right? It's different types of inputs and outputs. Natural language is what we're, I think most familiar with nowadays, is a foundation model that's trained on language, right? So you just feed it human language, whether that's English, whatever, you just feed it language. And then the model itself will generalize and understand language. That's the goal of the foundation models, to understand languages. I don't know if has anyone ever played with a base model? Like a base foundation model? Not the like an instruct version, what was your experience like?
It doesn't really listen most of the time.
It just doesn't listen at all, really, right? Just kind of spits out gobbledygook, kind of rephrases your question sometimes. It's not, what you get is unexpected usually, right? Again, because it's not the idea, again, the foundation model just understands language. You gave us some language, like here's some more language, right? Let's throw this back out at you. So it's kind of fun. If you haven't played the phone, I definitely recommend you do it. You can do it in the small scale ones. And then audio and speech as well. So again, you have models that can understand audio or speech and generalize. Some of these are these are a little bit more exotic, I would say, at least at this point in time. Multi-scale diarization decoder and like a T5 text to speech. Types of models, just high level.
Where would be Gemini from?
What's that?
Gemini?
Well, Gemini, like Google Gemini.
Yeah, what would that be?
So like Google Gemini is, there's probably a lot under the hood there. But I mean, I'm not 100% sure of like all the different parts of what's in that, but of course there's a language model associated with that, right? So Gemini is really just like, and I think it was like an application layer to access all these different types of models potentially that are behind the hood, right? It's like there's essentially families of models behind this, and right, depending on what you're asking for. So you can ask Gemini to generate you a picture, right? If you ask it to generate a picture, it's going to send it to one of these multimodal type models. If you ask it to give you a screenwriter or playwright, it's going to send it over to natural language foundation specialized model like that. So really, you're talking about like almost agent type question. Anyone else got big? Yeah.
How do we know that Gemini is more than one model and not just one large instruction to the multi-model?
Who wants to answer the back here?
That's what I was going to say. We use Gemini quite a bit actually, and it's a model family. So the other distinction to make is Gemini the product versus Gemini the model. If you go to like gemini.google.com, that is a product with lots of intermediaries. And it's different than like the instruction tuned model that if you're in Vertex interacting with it, Gemini Pro 1.5 or whatever is a specific model in the Gemini family. But they have the low end of like Gemma that are meant to be fine-tuned in open source all the way up through their pro models, which are quite a bit different.
Like imagine for image generation and video recognition things, like it's a mixture of excerpts with this like router on top of it.
That's what these good questions. Yeah.
Yeah, my understanding is Gemini Pro itself is also multimodal, so you can put in image and text at the same time and then get an answer out.
Yeah, mixture of experts kind of model and also multimodal. Yes. Yep.
Maybe I'm missing something. I thought multimodal was more about the training than the output.
Elaborate a bit. What do you mean by that?
So the magic, let's say, is that when you train it on all the text in the world, it gets to this level. But when you add audio, train the same model on text and audio, it's actually better at text. And you add video and it's actually better at text. You add radar and it's actually better at text. So that's my understanding of what multimodal, or at least one of the exciting things about multimodal.
I mean, yes. So I mean, I think if you kind of look up what the definition to this is, I think it's still pretty fuzzy, right? Because you've got a lot in terms of it looks at how the training. I agree with you. It's how it's actually trained, right? The inputs to the data, how the model, the inputs to the model itself, how the different inputs and affect what you're trying to do on the output wise, right? So if you look at like, right, you've got a text portion of that, but also the image generation portion of that model, two different inputs. The idea there is to come out with one output, right? Depending on what that output is supposed to be, right? So it really is, like you said, about the training. It's like, what are you putting into it, and what's your end objective to improve or to hit? So yeah, I mean that's a good way to look at that too. I mean that applies. So I think it's safe to say that right now, in terms of the large language model, well, in terms of the foundation model space, there's a lot of just research across the board of what can you plug into these things and what can you get out of them, right? And so I think that's ever evolving. So I couldn't find like a really good, in my opinion, like it was a solid definition. This was just kind of the way. So I think the simplest way for, depending on the audience, what would understand.
So the way I'm thinking about it is LLMs have taken over so many different models, right? Because they're just emerging capabilities.
Yeah.
Well, if the LLM is taking over lots of stuff and the multimodal LLM is better, then nobody's going to do single mode LLMs in the future, right?
Right.
Every LLM is just going to be multimodal.
Multimodal.
And obviously you may train it to output images or output text or output audio, but as far as the training, I'm guessing everything's going to go that way.
Right. And when in that case, when you say multimodal, you're talking about like the distinct types of data coming into the model itself, right? Like are you talking about data formats? Are you talking about types of data? Like, yeah. Is that what you're referring to when you mean like multimodal LLM kind of thing?
I haven't heard anything about it caring about data format, like GIF versus JPEG or WAV versus, other audio files. I don't think it cares about that, but I do think it cares whether it's audio versus text.
Versus text, yes, absolutely. Okay. I want to make sure, yeah. I'm not missing something. Discussion. Okay, anything else? Any questions on this one? Okay. All right, we're finally getting to the introduction slowly. Get to the meat of this thing in a second. Pre-training versus fine-tuning. I think we've already kind of hit on this at the point, right? Pre-training is the process of creating a foundation model. It is essentially taking large data sets, whatever they might be, feeding it through in a self-supervised way, and having, at the end of the day, something that understands, something that has a good understanding of language. Let's say again, let's keep with the language idea because I think it's easily to kind of relate to. But it can also be something that just understands images, right? It can be something that understands any kind of data, audio data, just generally. Fine-tuning is now taking that model and giving it a purpose, right? Having it good at being instructed, being good at coding. Like if you were to code llama, right? The idea of that is taking the llama foundation model and making it good at coding, right? It should be a coding assistant. ChatGPT, taking the GPT foundation model and making it good at conversational type, right? Or generating text of sorts. So again, pre-training versus fine-tuning. So in most cases, most companies are just doing fine-tuning, right? Foundation model training, pre-training is extremely costly in most cases. Talk about why. Fine-tuning, on the other hand, is a lot more accessible. It's so accessible that in some cases, depending on, again, how specific your use case is, you can do it on a local laptop potentially. All right. But it's just a lot more accessible, a lot more cost-effective. And it really gets down to, again, what you're trying to accomplish. Because if you've got, like, for example, your use cases, I want to build an application that understands legal documents. right? So I can take a foundation model, or I can even take a fine-tuned model and fine-tune that further, right? To really be good at understanding legal documents in stock index. I don't know, right? Something like that. So be very specific. At that point, you've got a model that's really good at that. It's going to suck at generating your movie plot. It's going to be really good at understanding legal documents. So that's the idea of fine tuning. So that's a lot more accessible. What I think where a lot of the use is coming from nowadays, but we had to start with a pre-training start. So someone had to say, okay, here's a model world, right? Thanks Meta for giving us a foundation model we could build off of. Like those at some point, right? That was kind of the access there that needed to happen. Obviously OpenAI was kind of the first ones that, well, they were the first people on the scene that kind of really advertised what they were doing. Okay, so again, I'm just like, I pretty much already covered this part where you take the language model, foundation model, and you can turn it into just specific things, right? Whether it's Q&A, summarization, coding, whatever. So I think we'll just go ahead and skip this right here. All right. Well, I guess before we begin, are there any other comments, questions about just large language models in general? I think this was just to serve as a primer, as an overview of what they are, or not large language models, but foundation models.
Really the difference between pre-training, training, is it objective? Does fine tuning have to have a non-self-supervised objective, or like what's really the continue, like how do you know you've crossed the line from
Pre-training to training? Yeah, I think this is the way I would look at it, right? Pre-training, I think it's kind of a misnomer to some degree. You're still training that model. The difference is, again, you're focused on just feeding it as much data in a self-supervised way to just get a generalized understanding of whatever that data is, right? There's pre-training, right? So now you've got something that's a foundation. It's something you can now build with. So now you can take that and move it on. So you cross the line, in my opinion, when the objective is very, like, of course, the objective was clear, the foundation model. You wanted to understand language, right? But now you say, okay, I want to understand what type of language, right? And you start feeding in that, then you start adding more objective to it in terms of like what it is. In both cases, there's an objective. In both cases, there's metrics. The model has to use metrics to figure out when it's ready, right? But I think it's the best way that the industry's come up with trying to explain what this is. Pre-training. It's before you're ready to use it for specific tasks. Does that help? It's semantic. Like a lot of this stuff, it's very semantic. It's a very fast evolving field right in the back there. Yeah.
I got to talk to one of the maintainers for Mistral earlier this year, and he very clearly laid out this question, which was there's different objectives, right? They're trying to give it an understanding of the language structure, so they're doing things like token prediction from a known block of text in the first phases. Later phases, they're doing things like RLHF to get a better quality voice to the right, or whatever that is. And then you go beyond that for instruct models or chat models or whatever you're doing.
And then you start in the training part. Yeah, exactly. Okay, there was a comment over here, then I'll go over here.
Okay, I was also going to say about that. So like, yeah, you can maybe change the distribution of the data that's going into the same sort of training pipeline. And then there are also cases like with BERT, for example. BERT was pre-trained on just kind of arbitrary text data, but then if you want to actually use it for a classification task, you have a completely different training paradigm where now you're just looking at a subset of its outputs and doing a supervised learning based on that. Yeah, something like that.
That's what, yeah, good way to explain it.
Yeah.
This is a more question for maybe further down the line, but when I've done pre-training, like I've just used data sets like FineWeb EDU was a nice clean one that I've used. However, like in my head, I've always had this paradigm that you gave an example, like if you really want to be good at, legalese, you save that for the fine tuning. But I have like a paradigm that if it sees these words that wouldn't be used or found as much on the regular internet during fine tuning, it will be better later down the line when we do our reinforcement learning and our fine tuning. And I want to get your thoughts on that.
I mean, I'll repreface. I don't consider myself like a modeling expert per se. I'm a platform guy. So yeah, I think
I want to just draw attention, this is exactly what he pointed out.
Yeah.
You can even have still a self-supervised paradigm for your fine tuning. It's just you change the distribution to accomplish a certain task, like making it good at legalese.
Yeah, I mean, yeah. Anything else? Any other comments on that?
I wonder if you could say that last part again.
Yeah.
Oh, I'm just repeating exactly what he said. Where
Yeah, understood.
every single thing that you wanted to know during the pre-training, and then the fine tuning, it's the exact same. It's still self-supervised. It's still within that paradigm. You haven't changed how it's training at all. You've just changed the distribution of data to be a lot thinner in just the slice of things that you care about for the downstream task, like being good at legalese.
So I must have misunderstood something because I thought that for me to do fine tuning, I needed input output pairs. Whereas for pre-training,
Supervised fine tuning.
Right.
That's a particular paradigm of it. You can do all sorts of them. It's just like he hit the nail on the head that the difference between pre-training and fine tuning really is more semantic than functional, because it's you can have the exact same data. You're just changing the distribution to accomplish a task. The task is the important part for fine tuning, whereas pre-training is like much more well defined.
So an example of where you might use a self-supervised learning task is maybe you pre-train your model on the whole internet, which is mostly, it's largely English language. Maybe your end goal is for your model to work on some language that doesn't have too much of a digital footprint. So you pre-train your model, it learns some understanding of the world, and then you fine tune on that language's particular syntax and vocabulary, and then it can be conversant in that language.
Is changing the temperature will be fine tuning?
What's that, Tim?
Change the temperature.
The temperature is changing the statistical, how rigid you essentially, how much variation you want in the output in terms of from a statistical perspective. So it's a way of adjusting potential distribution for the output, essentially. Does that make sense? A little, like, it changes how rigid the model is going to be in terms of what, because ultimately, right, if you talk about temperature for a large language model, you're just talking about it's generating the most probable, the likely most probable next word or token. It's supposed to come after what came before it. So because the temperature changes, what's the probability of it being more random versus more kind of falling back into how it was trained for on that. That's the best way I could explain that.
That's a hyperparameter, right?
Yes, that's a hyperparameter. That's an app, like, not really a hyperparameter. It's almost,
For its own, right? It's a generation time parameter.
yeah, yeah. Okay, Dan.
Yeah, I just, with all this discussion, wanted to bring up so with AI, everything's cyclical. So this discussion of like pre-training and fine tuning is going to happen over again. So the internet changes every day, every month. And so we're going to have to pre-train again next month or, every so often. And so
The flat earth, it's on the back of a turtle and this turtle's all the way down.
That's it. Talks over.
it
That's
happened once. It's going to happen over and over.
that's yeah.
So like all the discussion about pre-training, is this like largely hypothetical, or do people find themselves using this? I guess to my knowledge, it's by the time we have reached the foundational model, the pre-training has already occurred, because it's pretty expensive to do that initial step. So for most of our cases, even iterative like SFT and policy alignment are gonna suffice. Is that correct? Are there reasons why we would go back and pre-train?
That's a really good question. The answer is yes. I think it goes back to like we're doing the loop here. We're like fine tuning ourselves here a little bit. It depends again on what is your objective, right? What is the objective for the foundation model, right? You look like in GPT, the idea there is to generalize, understand human English language to its fullest, right? Again, if you want to say, well, that's a really broad task, right? Very expensive to do. So again, if your task is a subsidiary of what that foundation model can provide, there's no reason to retrain it. But you also might not get great results too, because of use case is so niche or whatever. And so it goes back to like this idea of like maybe you actually do provide a foundation model that is actually trained on a much smaller scale of data, right? It's very more targeted, it's much more targeted. So we're back to training. Again, semantics here. Language is fun. But like that the task might be what the objective might be. So there is opportunities for you to retrain a foundation model because you might again want it to be very specific. Also, too, when it comes to like companies, they might have a lot of proprietary data that's not available to the internet, that's available to them, that they now want to create a foundation model for and use internally for building other things off of. So it depends again. Like, so yeah, that's a really good question. That's really good. Yeah. So it's very cyclical, right? This is awesome. Did not think it would take, 30 minutes to get to the answer. This is great. Like, I love this.
You want a discussion?
I did. I asked for it. So this is, okay, we're gonna be here till like 10 o'clock tonight, guys. Here we go. All right. So no, actually this might get really boring. That might have been the most exciting part of this whole thing. So let's talk about computational demand. Let's talk about, okay, if I had to train a foundation model. And again, I think this is also kind of subjective, right? Because your foundation model can be very small, very targeted. So you don't necessarily need everything we're going to talk about, but you'll probably need a good part of it, right? And we're going to talk about, because you do need abilities to really be able to kind of process data, model train, do some kind of inference, and you have networking demands. So you've got a lot of different demands, no matter what, they've got to be satisfied in some way, shape, or form. All right, so kind of just high level again. This is ML in a nutshell, really. There's nothing crazy here. You're talking about the foundation model training process. It really doesn't vary from, I'll call it traditional machine learning training, right? You have data collection, curation, you do pre-processing. When you talk about data collection, right, again, that's the question of what data you want to use, pre-processing. The case of like, well, it depends on the data type, but again, usually involves cleaning, tokenizing, formatting the data for whatever the model's going to do. Talk about model selection now. So I think in the use case you brought up, right, if you're on a foundation model, you probably might be designing this model from scratch. You're going to put together your own architecture. You're going to figure out, I want to put it together like this, right? So you'll use whatever you want to build that model and how you want to build it. Or you say, okay, you know what, I think, Llama 3 is great. Let's use Llama 3 as the base here. We'll use that as our selection. And we'll use that same architecture. Train it now on this, change out what data looks at. So there's kind of that example there. And then training, right? Going through and processing the data, tweaking those gradients and updating model parameters. The key here, and this is why a lot of this has become feasible, right? One of it is the advancements such as GPU architecture in general. GPUs, as we all pretty much know, are pretty critical for deep learning and have been critical for deep learning for some time now, right? So you talk about the architecture for foundational training, talk about things like parallel processing. This is inside of the device. Now we're talking about parallel processing within the GPU device, right? Lots of cores to do that. Talk about high bandwidth memory. So there's been a lot of, again, advancements such as memory bandwidth. Just work for Micron. They build the memory that NVIDIA uses on their compute stuff. Technical term. Again, lots of advancements there for high bandwidth, what you can allow through how much data and throughput you can allow and everything that way. And then obviously now we have this idea of tensor cores, which NVIDIA pioneered in terms of dedicated hardware that's just for doing that types of computations that are required for deep learning. Because again, foundation models are just another example of deep learning. And we talk about deep learning in a general sense is just really, really convoluted, really complex neural networks, right? Questions on that?
Yes. In a modern model, what kind of operations end up on the tensor core versus on the GPU? Like, at some level, it's all matrix multiplication. What makes a specific matrix op specifically sent to the tensor core rather than the general GPU cores?
Like dissect that simply. So when you're going, so model architecture itself determines a lot of what type computations need to occur. When you are, we're getting to the really low level here. When you put together the model architecture itself, specific parts of the model, say talk about like the transformer part of a model, parts of that are better optimized for tensor type operations versus, let's say, like maybe some more of your, so when you're talking about model architecture and building these models from the ground up, a lot of the thought process and the optimization goes into what parts of it need to be sent to what parts of the hardware. And that's built into the models themselves. So it's not like when you do unless when because we can get really deep here. We're talking about, like, say, if you use PyTorch to build your model, right? There are so many layers of abstraction that happen between your code to what actually gets put on the hardware, right? You're going from the Python API down to the Torch to C++, well, CUDA. There's the CUDA part in there too, which is also, anyway, you build through that whole layer, all those layers of abstraction. All right, once more, okay, I've kind of like lost my train of thought there. There's a lot of just in general when it comes to generalizing these models, there's just already been a lot of forethought into how does this API at this level, what should it do? How should it, what part of it should be sent to which part of the hardware? I don't know, that's the best kind of got for you there. I don't know if I have a really good deep. Matt, what do you got, man?
Yes, that's hardware guys, right? So you're probably thinking a little bit too much about how, like, once you start working in semiconductors, you always think about how individual electrons are sent through these itty bitty, copper wires down into the CPU and how it switches gates and other things like that and how computers work. But that's probably not what you're really asking. Essentially, the GPU, say it's an NVIDIA GPU, they have different kernels. These kernels are doing different, one's doing addition, one's doing subtraction, one's replacing, one's nulling the value.
Kernel is a software concept. I thought kernel's like a CUDA kernel, which is not a hardware concept. Core is hardware, but kernel is software, I thought.
Yeah. And so when you build your model, like if especially if you optimize it, which is the whole point, and so you send it through like TensorRT, you're gonna essentially give a graphed optimization of the model, which is gonna predefine the kernels that the model needs to run. And those kernels will map to different parts of the GPU based off of which part of the GPU will best run the kernel.
That all makes sense. But like, which operations get sent to a tensor core and why?
You can find out really easily. Just like import Torch, build a teeny little model, and then send like one layer of the model to GPU, and you'll hit that error of like multiple devices detected, CPU and GPU. Just figure out which are the ones that you need to send to the GPU. Let's send them all, and then get rid of some of them, send none of them, and then add some of them. Right? You can figure it out pretty easily, but generally, it's the linear layers. It's the same layers that you would change if you were turning that model into a LoRa. Those are the ones going to the GPU kernel.
Yeah, so essentially all the matrix multiplication, that is going to go to a tensor core because that's what those are really built for.
But that's the easiest way to test which ones, like if you're building a new, maybe like a fully partially connected, so fully connected linear layer, right? You can test whether you should or shouldn't send it to the kernel by just to GPU, to device, and if it errors,
So
it
that's
shouldn't go
CPU
there.
versus GPU, but I mean like GPU versus tensor core.
Oh, okay.
That's where it's like less clear to me what the tensor core is built to be specifically good at. Is it matrix multiplications of a very specific dimension, size of your memory?
So the basic GPU is really just that multi-parallel processing built for graphics.
Right.
And so because you're doing all these multi-parallel processing, it just happens to be good at matrix multiplication. But really where the tensor core comes in is it comes and it's able to format the data that's coming in into actual tensors. And so that's how it's able to get into it. I feel like we've probably gotten really deep into.
Yeah, sorry, we can say it's all the right, all the, it's like, that's just stuff.
That helps. We can always talk after as well.
Yeah, that also depends on whether you're talking about the DNN layer or the CUDA layer. They're two completely different abstraction layers. We have one a lot less control. So it depends.
It's like I needed to take a class back. I mean, I wish I was a CUDA programmer because I feel like I have a better understanding of again, because like we talk about what you're asking, that's really what you're getting down to is telling you exactly what makes sense, right? And Matt's doing that. I mean, a really good job explaining that. Obviously, there's just different parts optimized for different things. And your question is how does it know that, right? When it builds the computational graph, what does it know? How does it know how to do that? That's right. I don't think I have a really good succinct.
What does ChatGPT say?
Yeah. We could ask probably some gibberish, but you're right. Who knows? Okay. Get through here. Okay, let's keep moving through here. So I mentioned high bandwidth memory, all these things, right? All right. This is where I kind of want to, I think we're going to get a little interesting. So I want to talk now about, right, different paradigms of parallelism. So when you're talking about how to train these different types of models, obviously we are limited in the amount of hardware you have available, right? Whether that's memory, CPU, GPU, whatever it is, right? So in order to train the models, if you, like for example, if you have to talk about the Mixtral 8 7B is like 70 gigs, right? I think it's about what it is roughly. Okay, so it's a big model in general. It's a mixture of experts. Train something like that. That's not going to, you have to have a GPU. All there is fit the model on the GPU and have enough RAM to actually do that. Or you have to split the model up. Right? Or when you're training a model on large corpus of data, internet, whatever it might be, you obviously can't fit all the data in memory. You got to actually split that data up and send it to different devices. And so we're going to go kind of through that idea, and then activation partitioning, which I'm not going to talk about, but that's essentially like being able to activate different parts of the model, right? Models are just stacks of different layers of things. You can activate different parts of those, and there's different types of parallelism that you can use, again, to activate specific parts of those, like sequence parallelism, context parallelism. I just linked in, this is really great. Like if you're doing this, how many of you guys have like used the Nemo image that NVIDIA offers? It's huge. It's kind of a mess, actually, to be honest. But unfortunately, the data scientists where I work really like it. So if you go to these docs, they'll look through this. They have a really good explanation. This is a lot where this is summarized from, is what these different paradigms are and how they work. We'll go through them, though, a few of them. Okay. So this is coming from those docs. So let's talk about distributed data parallelism. So in this case, you've got 4 GPU devices. You've got a big global batch of data. This is going to kind of move. And you've got these micro batches that get split up, right? And then what you're seeing here in the green is the forward pass of this data through the model. So in this case, it's a really simple model. It's a 3-layer model. You're going to forward pass this data here. And then once it hits the end there, you're now going to do the backward pass, right? So yellow there for the backward pass. Keeps going through here. It's moving a little slow. At the end of the day, we'll talk about the gradient. I'll reduce algorithm here a little bit in there. But the idea is, again, the key part of this diagram is to understand that when you talk about distributed data parallelism, you're talking about taking your large data set and distributing it across devices in micro batches. We'll talk about how you sync all that back together. After this, we talk about collective operations. All right, so pipeline parallelism, to think of this is a paradigm of model parallelism. So in this case now, the model itself is actually spread across GPU devices. So you can see like layers 0 through 8 are on GPU device 0, 9 through 17 are on 1, et cetera, et cetera. Okay, right? And so as you're processing the micro batch of data, each one of these micro batches, they go through the exact same process. They're going through the data is moving through each of these, and it's the job of now to pass this the output of each one of these layers to the next layer to continue the propagation process both forward and backward. All right, and so then tensor parallelism, you've got this transformers block here, but like again, we talk about tensor parallelism, you're really talking about intra-layer. How do you like break up a large tensor, it might be also too big to fit through the device. So when you got input X and it goes through all these activation layers, fast, sorry, let it come back. Since you're just breaking up that whole tensor itself into smaller chunks. You see this more at the GPU device level versus actually spreading across devices themselves. You see this inside the GPU device. I won't spend too much time on this exact one, but this is, again, if you have like a transformer, this is what's happening kind of inside of here.
Is that just like block multiplication of matrices?
Absolutely. Yeah. It's just exactly. So the real big thing too is like pipeline parallelism and distributed data parallelism is what you really deal a lot with when you talk about those big models. This is more handled at the device level. This is already a lot of your libraries. This is already taken care of, and the device takes care of a lot of that. All right. Hyperplug. So if you want to learn more about distributed machine learning patterns in general, I really recommend this book. Dan knows this guy. Harry Tang or Yuan Tang. I even quoted there. It's kind of fun, but it's a really good book. It's just generally about distributed machine learning patterns. He does use TensorFlow as an example, which you might throw up in your mouth. But the point is, it's a good book in terms of understanding how do you build distributed and reliable machine learning systems in general. So general book approach to that. So I do recommend that. So grab that. And when these slides are up, you can grab the link off here and go buy Harry's book. So Harry's book, yeah. So all right, let's talk now. Let's kind of move this. Are there any questions about? We're going through this. Okay, this is where we're getting data center infrastructure for large language models. Okay, so when I put LLMs here, I really meant foundation models, but LLMs are kind of the foundation model flavor we'll talk about. Power management, scalability, redundancy. These are all just general things, right? And the reality is we're going to show you this. There's a couple ways companies do this. They either roll their own data center because they've got a lot of money. That's Meta. Look at their use case. And then there's other companies who don't want to manage that, and they use cloud vendors to do something very similar, right? They're going to use cloud vendors, though. They're going to build their own virtual data center, and it's not based on auto scaling usually. She's talking about like capacity reservations, things like that, because they'd rather pay a cloud vendor to hold those resources and manage those than do it themselves. A lot of this comes down into like networking is a big deal here. There's been a lot of advancements in just network interfaces to make a lot of this possible. So when you're talking about, again, moving this amounts of data across not just devices that are inside the same node, but devices that are on distributed nodes all throughout the system. And when you start looking at what it takes to train one of these, you're talking about tens of thousands of GPU devices inside thousands of nodes, right, that are spread about. This matters, and this is a huge bottleneck for this training process. So being able to have a network that can handle type of data is huge. So here's an example AWS has in terms of how do they solve this problem? How do they allowed high-speed data throughput in their processes? So there's a couple different layers here. I'll go through it. This is fairly interesting. Now, this is not something you can just like go and go to your AWS account and grab what they call an ultra cluster. Right? There's a little bit more to it than that. But the showcase here is if you actually Google P4D on AWS's site, this is one of the first things that comes up because they're kind of wanting to show you, hey, look what we can do, right? Look what we can do for you if you can afford it. So you need a layer here for storage, right? So FSX is again, high-speed data layer that acts like a onboard file system that allows really high-speed IOPS. Again, right? Talking about a lot of throughput and data. In this case here, this image, I've got all these P4Ds and they're all distributed out. Again, the problem really is not how do I communicate data inside the node, but how do I get data across the node? So the technologies that EABS said, they have a proprietary network interface called the EFA, Elastic Fabric Adapter. And that EFA device allows operating system bypass so that the GPUs over on these eight A100s on this P4D can directly go through that network interface, bypass the CPU and talk to the other devices. So they don't get bottlenecked on dealing with the CPU. Okay. So this is a huge way to help reduce that latency. There's also some physical considerations here. If you have one P4D in like one sub-region, like we'll talk about AWS, right? One availability zone, and then you have another one over this availability zone. There's probably a lot of distance physically between those two compute nodes, right? So again, too, when you're talking about optimizing your processes here and how you want data throughput, that's also the consideration is what availability zones and hey, can we get you closer to even things in the same data warehouse? It's same. So that all matters. It all matters when it comes to throughput. Any question on this? This is just got a high level of ultra clusters, but that's their concept of it. Now, Meta's Gen AI infrastructure, they completely rolled their own, which hats off. Okay. So very similar. They have this Grand Teton architecture, which is similar to a P4D. It's got 8 A100s in it. It is essentially their own version of this box. And they've got a couple different, well, at least this article that they released to the world, they showed about 2 different versions of their whole stack. So, hats off to Meta. I mean, I know I have a lot of money, obviously, and, but like, they at least are like putting it out there for the world to see these things a little bit, right? Giving a little pull back behind the curtain. So they did go with like an open design. So they have this Grand Teton. I've got a leak scenario that you can check all these things out. But like Grand Teton is their own, again, how they build their hardware, with how they build their own compute systems. They use OpenRack, which is an open source. So right, like this is literally like if you've ever managed a server farm, which I haven't, you probably know all these things are really well. So anyway, the point is they use 2 different approaches to this. They use RDMA with these other chips like the Arista and the Wedge and the Minipack network interfaces, and also using the Quantum 2 InfiniBand fabric. So these are just 2 examples. Go ahead and just read this article. It's linked here. Get deep into it. It's pretty fascinating. But the point is, they also did their own homegrown Linux file system to make this thing work, right? So again, they have their own version of like FSX, right? That's really what it is. It's FSX is AWS's version of their own Linux file system. So, right. Okay. Just want to kind of get that's kind of like hardware overview. Who's there now? Yeah. What do you got for me?
You talked earlier about the different types of parallelism. We're talking about a distributed, like a multi-node training job. What type of parallelism is used within a node, like across those 8 GPUs, and what type of parallelism is used between nodes?
Got it. So great question. So we're jumping into collective operations next, which is the next part of this, because paradigms of parallelism are not complete without how you actually collect all that data. The answer is it's the same. The question is how fast can you do it? All right. So it's all about, so if you're like if you want to do model parallelism, right? You're going to parallelize the model across different parts of different GPU devices. In theory, you can spread that across several nodes with several devices inside of it, right? So if I have 2 P4Ds, 8 A100s in each one of them, I could, in theory, split my model 16 ways across that and do that.
If your whole model fits on.
That's if your whole, exactly. Like if your whole model, that's assuming that's slicing your model up. That's assuming it's so big it has to fit across those, 80 gig A100s, those versions of it. But obviously you're going to run a lot of data latency, and your bottleneck, in most cases, the bottleneck here is actually going to be networking. But that makes sense. So it doesn't matter where the node is. The idea is to treat them as if they're all under the same hood, best you can.
Like, what is the specific type? Like, isn't it tensor parallel within a node and then data?
Oh, yeah. So tensor parallel is like within the device, actually, like at the core level, the GPU device level, versus, I'm sure there's a use case where you do tensor parallelism across GPU devices, but I don't think it's less common because the models aren't that big.
Because it's the opposite of my impression, is that like tensor parallelism is the only kind of parallelism you use across GPUs within a node.
So you may be thinking like how the data, how the data. I mean, yeah.
But I've got a model that's too big for one GPU, got a node with 8 GPUs on it, so I can't do like DDP. So I have to split each of my tensors across.
Yes, you take the model tensors, you
You
split
don't
them.
want to do parallelism because then only one thing's running at a time.
Yeah.
So you have to do tensor parallelism within a node and then DDP across nodes.
Well, as long as we're talking PyTorch, sorry if my knowledge may be out of date on this. There's distributed data parallel, but there is also data parallel, which is within the same node. So I think there's like
So it's just data parallel at both levels.
well, so data parallel you can use on one node with multiple GPUs. DDP would be between nodes.
Yeah, we'll talk about DDP in a second. I mean, I think that's where I'm just misunderstanding your question, but like,
Data parallelism doesn't work within a node if the model doesn't fit entirely on a single GPU. Right, so in order to shard across GPUs.
Right, so if you assume that the model fits on the GPU, but you have more data than can fit on the GPU, you could use data parallel to.
That's not really true of like any current foundation model, right? Like you need at least 2 H100s to fit pretty much any modern unquantized model at training time. So when you do that, always tensor parallel, or are there other options?
so that would be, what you're saying is that's a model parallelism paradigm.
Right. Right. Which one is it?
Of the model. Okay.
Well, I mean, you have the networking bottleneck regardless. So does it really, how you slice and dice it as long as you have that bottleneck?
Yes, it does. Because if you go pipeline parallel, then you're wasting compute because only one thing's doing something at a time. You can't go data parallel because the model's too big. The only option left is tensor parallel.
You can mix and match these paradigms. So that's like, depending again on what you're trying to do and what your objective is, that's how you determining how you're going to split this thing up. So you can, I hope that's where you're heading with things, but you can definitely split your model up in a pipeline parallel and also parallelly process those layers as well in a tensor parallelism.
Yeah, sorry, we can move on.
Let's chat afterwards. I think good. All right, it's collective operations. All right, so message passing interface, who's heard of that? When everybody probably has, right? Well, half of us have. So that's like a standard design to function for any kind of parallel computing architecture. So you can see that used not just GPU applications, you see that as well as in Spark applications, things of that nature. Anything that's parallelized or distributed, you'll see like you can use an MPI implementation of it. NVIDIA Collective Communications Library is essentially NVIDIA's way of actually providing the primitives required to work within their own devices for doing operations that kind of bring the data back together. That's kind of the best way I would describe that. So there's several of these types of collective operations. At a high level, you've got all reduce, broadcast, reduce. So let's scroll down here. All gather, reduce, scatter. All reduce probably it's probably the easiest to understand. We'll talk about ring. All reduce here in a second when we talk about distributed data parallelism, because this is where we bring these things together. Simple level, but like if you're looking at these different collective operations, all reduce is a way of saying, okay, I've got, when you talk about these ranks now, this is kind of going into the NVIDIA's nomenclature that they use. Ranks can represent a lot of different things. When you're talking about like a fleet of GPU devices, the rank will usually indicate, like a global rank will indicate a specific device on a specific node. And then just a rank by itself will specify a device within a node. Go to if you want to look at this and get to the depth, go into the nickel library here and kind of read up on that part of it. But in a nutshell, very simply, let's say we have 4 devices here, right? Rank 0 through rank 3. In all reduce, what you're trying to do, you're trying to take all of the data all across all these different devices. It's all different, bring it together into one way, right? And then how you actually reduce that data, whether it's a sum, min, max, average, whatever it might be, that's a separate operation. But as part of that operation is you determine that what it is. But the idea is just, again, all reduce is taking distributed different data, bring it same across the whole, all of the devices. That makes sense. Broadcast. We'll just do all reduce broadcast, and I think, yeah. So broadcast is, okay, I've got a specifically input of data on a specific device. We'll call it the root device. And we now need to take that data and pass it to all of the other devices in the fleet, whatever we'll call that, in all the different rings. So that's a broadcast. So it's just broadcast that data out. Instead of all reduce, if you have reduce, it's about taking all your varied inputs, again, taking that and actually just reducing all of those varied inputs to specifically one buffer, right? So one specific root rank in this case, because again, I'll show you that. I got to scroll. All gathered. You got your different. In this case, it's strange. You've got like different data across your different devices, and you're again just trying to distribute that across all your different ranks there. And then reduce scatter is kind of the opposite of that. Okay, so this is really when you're looking at these different collective operations, you'll see all reduce a lot go into that. That works well with distributed data parallel, which is probably, again, with my experience, is the most common. We'll see. In fact, so instead of me trying to come up with a really cool outline or like my own graphic for this PyTorch distributed video series is actually really good. If you guys want to just like dive into it, but I'm gonna just like talk over. This guy's.
So when we distribute this training job to let's
just go through it here. So, all right, so let's take collective operations. Let me pause real quick.
this has its own local copy of the model.
Collective operations and tying it back into paradigms of parallelism. In this case, we have distributed data parallelism. So we're talking about, we have, this case, the same model that's distributed across 4 different GPU devices. Model can fit in memory. And then we have our optimizer spread across there, all of them. Point is, we're gonna run batches, micro batches of data through each of these GPUs. We'll talk about it. Speed it up just a bit.
Tell us who's speaking.
Yeah, I will. Let me just let's start there in a second. Okay, so that's the setup. This is I'll go back to the start here. He does the entire series, the distributed data series on here. Okay. So the PyTorch paradigms here, like data loader and things of that nature, and your input batch and distributed sampler. The idea is here, you got all of your data. You're going to use the distributed sampler to break that out into these micro batches of data that are going to now be processed. So now the idea is, right, you got to be able to, you have 4 times the amount of data. You can't fit it all in one GPU. So you end up running those micro batches up through, passes through here. So we saw this in, distributed data parallelism. We've got these, now at this point, we've run 4 different micro batches of data on the same model. So the weights, the gradients that are calculated for each of these models are now different. Right? These are 4 different models that exist at this point. So because we ran different data sets through the same model. So now that we've calculating this, we have 4 separate models. The idea now is, how do I get this back to synchronize to a single model? So this is where all reduce comes into play here, right? This is a specific flavor of all reduce called ring all reduce. It minimizes a lot of some of the bottlenecks. The idea here is the system begins to pass on these gradients to the rest of the system here. The end goal here is to end up with the same model, same gradients on each model on all devices. So at this point, then you now have the same model on each device, and that's just one iteration, that iterative step, that process that you just continue. Very, very common distributed data parallel. That can be used in a lot of, I think models I've worked with for the teams that I've served. This usually just a very strong size. Any other experience? I feel like you've got a lot of experience doing this, or
Oh yeah, I mean I worked with Tanner on making the FSDPQ LoRa PyPy package, which uses a drop-in replacement for DDP called auto wrap. It differs in that it's not just passing the model, it's passing pieces of the model as they contain the tensors, like during training. It's pretty cool. But what that allows you to do is for those cases where the model doesn't all fit on one GPU, you can chart both the model, the data, and the tensors as they are computing. As they go through it, it's pretty sick.
that's sick. So
I have a question.
yeah,
So is what we just watched, would that be called one epoch or epoch or however you say it? Or is that
one step.
so what
So
would
one pass the data. So one pass the microbatch the data, right? So you've taken your data set, right? You've split it up, and now so an epoch would be the model has seen all of the data, right? That's not what that happened. What we just saw there was one step that we broke the data up into 4 different pieces, passed it to those model for that's just one step. So it went through it, just that step.
we're breaking up the batches into smaller batches?
Yes, that's just like one step. So yeah, so until the model has gone through the entire data set, you haven't reached the epoch. Then you keep doing that in a shuffled way. Then you do another epoch, and you'll distribute the data a different way now. Do the same thing.
So you can have an epoch go on indefinitely.
So an epoch is done when the whole data set has been passed.
Oh, I guess it's about that. You can get all the way down to like, oh, there's just one data point that hasn't reached that node yet or whatever. Like,
Epoch, yeah. And then you start over again, but you now shuffle the data a different way. Ideally. That answers your question.
yeah, I think so.
It's gonna add one thing that's really nice about ring all reduce is that it allows you to update your gradients asynchronously. Because the other way of like managing your gradients is that it's all handled by a single node, and every GPU will pass its gradients to that master node. But then you're waiting for all of your GPUs to finish computing the gradients before you back propagate. So you end up waiting a little bit. So that's why this method's kind of cool.
Questions, comments? Okay, we're getting to the end here. I think we're running out of gas a little bit. So
My
Yeah,
laptop's
right.
running out of power.
yeah. So let's this has been good. So I'm gonna like kind of breeze through the rest of this. In fact, I think that I do put a plug next. Software frameworks for foundation model training. There's so much software right now coming out in general for libraries. I think if you look at, again, just for the training side of things like Xformers, Accelerate, Nemo, DeepSpeed, Megatron, LM. These are all, some of these like Megatron LM is what like Accelerate and Nemo are built off of, for example. They're like the underlying things. Again, Megatron LM comes from NVIDIA, Nemo comes from NVIDIA, Accelerate comes from Hugging Face, DeepSpeed comes from Microsoft. But again, at the end of the day, like a lot of these things, and Xformers is kind of like your bleeding edge version of PyTorch, but they're coming. There's different ways of doing this, right? And it actually becomes quite, right now at least, the mixing and matching of these, of like, let's say how you train, how you quantize, how you serve the model matters. Like it's kind of like a key. I'd say like I would call, you got to make sure these things line up and are compatible, because there's the libraries themselves not really converge. I say, yeah.
I would make one switch because Xformers is like way more research focused. They have an actual PyTorch++. It's not called that. It's called Fair Scale. Like that's what they use to develop Llama 2 and Llama 3, to get like the parallelism within the columns and the rows. Like they literally have those for specific linear layers dealing with those portions of the tensors. But I don't know if I'd say Xformers is fantastic for training unless you're doing research.
Yeah, and exactly what kind of research you're doing. A lot of this, at least again, the researches I have at Capital One, this is a sort of a lot of the similar things that are being used today. This is like what they're asking for, these types of things.
Actually, on that note, how did Capital One decide that training foundation models is something they wanted to do?
Wish I could tell you. Wish I could tell you. I have to bite my tongue quite a bit to this whole presentation.
Does that mean it was some executive's idea?
No comment. So let's move on here. So I'll put a plug in for Chris and Matt's book. I don't know if you guys have read this. Like, I would say if you guys want a primer to a lot of these things, read this book, right? If you haven't picked it up, Chris and Matt finished this book just recently, right? It's great. It's a really good. I feel like you don't have to have a ton of ML background to make this accessible. You probably will have had to work a little bit with libraries and things to kind of get these up and running. You do have a GitHub repo. I don't know if you have any Docker images that can just be pulled down quickly to make things run, but I do know you provide, hey, keep track of your libraries and things. And obviously providing like things change a lot right now in space. So it's hard to like say this, and this, but
we can make some images.
Yeah, stuff out there would be awesome. So, all right, I'm gonna just finish up with this. So, at the end of the day, you got all these compute clusters. You've got to connect all these nodes together. We talked about networking, different ways of also kind of like bringing these things together. If you've been in the research field for a long time, Slurm is probably something you've seen before. It's definitely, high performance computing paradigm, allows you to like do workload management. That was very common for a lot of years. Kubernetes is now on the scene. It's what I'm most familiar with. It's again container orchestration, and you're able to adjust high performance computing workloads to it, right? With a lot of open source libraries and things of that nature to make it work. LSF, I honestly don't know if anyone's even using that anymore. That's pretty old, but that was IBM's old platform to kind of do all these things. So I'm going to just.
Slurm is like here. I think Slurm is like based in Utah, like American Fork, which is cool.
I didn't even see you here, Eric. I see. Yeah, Slurm is here. Yeah. So it's open source. You can and you can use it. It's available. Kubernetes is also open source available. It kind of just depends. Then again, we're talking about how do you bring all these things together. There's some ways to do it. I'm going to end there because I think we're all tired. But I appreciate it. Any questions?